Okay, welcome back everyone. So let's wait for 5 more minutes to see if anyone joins. Then we can start. We are planning to start by 3:05, right? Okay, so welcome back. So this is NOC EE-62 NPTEL tutorial on basic electronics. The course instructor is Professor Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. As you know, the course duration is of 12 weeks. We are at the 11th week, so almost one more lecture after this will be remaining. So again, I will reiterate that please join on time and every Sunday 3 to 5 if you desire to attend the session. Okay. So there are some basic prerequisites which I would like to reiterate again, that you are expected to at least have gone through the lectures of last week, and also at least have tried to attempt the assignments posted, right? This will help you to grasp the concepts discussed in this session. So please keep your microphones muted all the time. And if you have any question, you can use the raise hand option, or I will give you some time after each and every topic to ask your query. Also, as it is a 2-hour session, at the end of the session, I will allot around 10 to 15 minutes to allow you to ask your general query regarding this session. Okay. So all the recorded lecture sessions are available on Week-11. Yeah. Just let me check once the internet connection. Okay. So what we will do today, we will basically discuss about sequential circuits. Okay. Sequential circuits. Last week we have discussed some combinational circuits. Okay, so this is our carry today. Okay, we will discuss some basic stuffs about these sequential circuits. So let me begin with what are these before we dive into the problems. So you see, you have your, suppose this is your system block. Okay, by the way, what are these? These lines signify multiple inputs, right? Multiple inputs or outputs. The more convenient way to draw these things is like with a single line with a slash on top of it. Okay. So your combinational circuits. What is the definition? Output depends on current inputs, right? Current inputs. No memory. Okay. So what about your sequential circuits? Sequential circuits. It has memory, right? First distinction with the combinational circuits is that it has memory. Also, output depends on current input and previous outputs. Okay. So how does it work? Basically, behind the sequential circuits, there are combinational circuits with some memory function, right? So if I would to draw, so this is your combinational circuit. Let's say these are your inputs, these are your outputs. So suppose you have something in your feedback, some memory action in your feedback path, right? Okay. So this stuff would then be your sequential circuit board. Sequential circuit block. Okay. So you see, one of the key aspect is that feedback. Feedback is present. Okay. So why do you need sequential circuits? You would like to, this is your storage element, right? So sequential circuits help us to store data, right? What do we store, by the way? We store ones and zeros. Okay, ones and zeros. This is binary coded information, right? So if we can store 1 bit, right? If we can store 1 bit, we can just replicate it and then get any number of higher storing device, right? 1 bit, then just replicate it to store larger information. Okay. So suppose you have a 1 MB. So you are most familiar with GB. Let me do it with GB. So 1 GB HDD. Okay. So 1 GB means you can, any memory, you can boil it down to some basic number of strings of bits, right? So 1 GB would be your 10⁻⁹ byte, right? And what is 1 byte? We have already discussed that 1 byte is nothing but 8 bits. Okay. So 8 into 10⁻⁹ bits. So if you can store 1 bit, you can just have this number of same building blocks replicated and you can store higher number of bits. Okay. So basically, unit storage elements are involved in higher capacity storage device. Now, you must have heard of SRAM, DRAM. Those are some different concepts, but building upon the same one, right? You have certain kind of memory. Now, the matter is how you can store the data. Okay. So it is storage element. Okay. So we will start with the basic storage element. What is the basic storage element? If you have gone through the lecture, you must have heard about this term, right? Latch. It is the basic storage element. Okay. So what are the kind of latches you have? You are familiar with SR latch, right? We will discuss both NOR version and NAND version. Okay. So how does it work? So SR NOR, let's say. So you have these NOR gates. Okay, let's call it R. This is S. And let's say the output is Q and Q bar. Okay. And then you have this kind of configuration. Okay. So you see, this is your feedback kind of thing, right? From output to input. This is, I would say, this is your feedback. Okay. These steps. So how does it work? You are aware of the NOT truth table, right? NOT truth table. And what is that? If you have two inputs, let me just show it in this way for the sake of completeness. 0 0 0 1 1 0 1 1. Okay. For OR you have all the three these cases 0 and here 1. So it will be just the reverse, right? So this is your NOT truth table. So how does it work? If I have to make a truth table out of this function, then let's say you have S, you have R, you have Q, and you have Q bar. Okay. Now suppose I am setting this as S equal to 0, R equal to 1. Okay. That means this is off for the first time. And this is, let's say I'm providing some signal to that input, some high signal, right? High means we have already discussed that what is 0 and what is 1. 0 is nothing but a ground. That means you did not switch on the terminal. And what is 1? 1 is your VDD, right? That means your highest potential you are giving. So how does it work? You see from the table, you can see that if any of the input of the NOR gate is 1, right? Any of them is 1, then the output is 0. So in this case, in the top case, the output will obviously be 0 and this will be 1, right? Because this is nothing but your Q bar. So if this is 1 and this is 0, so you see this 0 is coming here, 0 0, you are giving 0 0, you are getting 1, right? So it is 1 and 1 1, you are getting 0, fine. So if your S is 0, R is 1, you are getting Q as 0, Q bar as 1. Okay. Now suppose you just switch it off. Okay. You make it 0. What will happen? If you make it 0, you see you had 1 here. So 1 and 0 will become 0. So 0 will remain, right? So if you make it 0 and you just switch the R terminal off, so your Q will remain 0, right? And what will be this? Q bar? Q bar, and obviously if it is remaining 0, as you did not change, so it will only be 1, right? So you try to visualize it in this way that you have two ports, right? In one port, you have given one input. So accordingly, your outputs have been set. Now, if you remove that input or you just switch it off, what happens? This value is stored here, right? So this acts as a memory state. Now, if I keep the SR latch, by the way, this is called SR latch. If I keep the SR latch untouched at this state, that means the output will remain 0 and 1 forever. If we consider everything ideal, right? So that means we were able to store information where Q is 0 and Q bar is 1. Fine. So this is how the storing thing works. Now, let me just remove this and make this combination. Say this is 1 and this is 0. Again, if this is 0, so your output, this is 1, so your output will be 0 and this will be, okay, I was doing the same thing, right? So just let me reverse the signs. So let me call this is 0 and this is 1, okay? So if this is 1, then output will be output of the NOR gate, any of the input if 1, output will be 0, right? And this 0, 0 would be 1, right? And then this 1, 1 will remain 0, right? Basically, the flow is if one of the our input is 1, output is 0, and 0 is going here, right? So this 0, 0, this is 0, this is 0, providing 1, and this 1 and 1 is providing your 0, right? So this way, if you have 1 and 0, your output will be 1 and 0. And again, you can check if you remove this to 0, if you change this to 0, output will remain at 1, 0, right? So this will also act as a memory state. Okay. And if you make S equal to 1 or equal to 1, you would see that you cannot predict the output. Okay. So what will happen if you make, suppose you had this state, right? Now you make this one. Okay. Then 0 and 1 will make this 0, and 0 and 1 will make this 0. Fine. And this will again change to 1, and again it will get repeated. Okay. So you cannot predict that. So we do not generally use this. Not used because of unpredictable nature. Fine. So this is how your latch works. Okay. So now how do you write the compact truth table? Compact truth table. You write SR, you write Q, you write Q bar. So your 0, 0 is leading to memory state, right? Or let me just write in a more conventional form. This is n plus 1. Okay. So it will be Qn. Okay. That means it is storing the previous state. That means it is working as a memory. Now, if you have 0, 1, obviously your output will be 0, 1. See, this is 0, 1. So this is 0, 1. And again, 1, 0 will lead to 1, 0. And 1, 1 is not used. Okay. So this is a compact truth table of your SR NOR latch. Fine. This can be made with NAND gates also. Okay. NAND gates can also be used to create SR latch operation. And how does the name come about? Name come about like this is your output, right? And this is your output, and basically you can consider S terminals this as your input, right? So if S is 0, output is 0, and if S is 1, output is 1. That means S controls directly your Q. So S sets the value of Q, right? When S sets means when S is high, your output is high. And when R sets, or I would say resets the value of Q. That means when R is high, when your R is high, output is 0. Fine. So this SR actually comes from the term setting and resetting. Okay. So this is how your SR latch works. Now let us go to the first problem. So what does it say? It says that the S and R in S bar and R bar inputs shown in the figure are applied to a NAND latch. Assume that Q is 0 initially. What is the plot? Which plot gives the correct waveform of Q. Fine. So how does this NAND thing work? Let us just again in the similar fashion, we will make a first we will see how NAND truth table looks like. If these are input, this is output 0 0 0 1 1 0 1 1, right? So 0 in this case, these three were 0, so these are 1 and this is 0. Fine. This is your NAND truth table. Now, what would be your NAND latch operation? You see your S bar, R bar, Q, Q bar. When S bar is 0, R bar is 1. What happens? S bar is 0, R bar is 1. That means, you see, if any of the input is 0, then output is 1 from the NAND gate truth table, right? From these three. So this will be 1, and similarly 1 1, this will be 0. So your 0 1 creates the operation 1 0. Similarly, your 1 0 will create the operation, the output 0 1. And what about your 1 1? If both are 1, now suppose if I just move this to 1, what will happen? The 0 1 will make the output remain at 1, and your 1 1 will keep the output remaining at 0. So it is nothing but a memory state. And in the similar manner, you can show that 0 0 is not used in this case. Okay, so this is your NAND latch truth table. Fine. So now let us see. So let me zoom it up, and this much we know, right? So now what we are asked, that your input is given like this, we need to draw the Q waveform, right? So the way to do it is, let me just draw some vertical lines, okay? Let me just draw some vertical lines. This is nothing but the time instance at which your one of the input is changing, okay? So these are the changes in the input, any of the input. So now just let me write down, this is 1, okay. Okay. So this is 1, then 0, then 1, 1, 1, 1, 1, 0, 1, 1, 1. Fine. So what is here? You have 1, you have 1, you have 1, you have 0 for R bar, right? You have 1 here. Again, you have 0, you have 1, you have 1, you have 1, you have 0 and 1. Fine. So now if we draw the Q, we just need to refer to this table. Okay. So what do we see? We see that when S bar and R bar is 0, 1, output is 1. That means it is nothing but the invert of this S bar, or we would say that whatever the value is of R bar is there, output is storing that. Okay, this 1 is heading here to 1. That means this 1 is heading here to 1 and 0 is heading here to 0. Fine. So what is the initial value? The initial value is 0, right? It is mentioned that Q is 0 initially. That means if I have to draw like this is 0 initially. Fine. Now what does it see? It sees S bar is 1, R bar is 1. That means it is in this state. So this will store the previous value, right? Till this duration, it will store the previous value. Fine. Just let me zoom it up, or let me just do one thing. Let me copy it and paste it here. Okay. So that, okay. So now you can see that till this point, it will store the previous state because both input are 1. It is a memory state. Fine. And now when 0 and 1 is there at the input, output will just follow the R. Fine. Till this point. Again, it is 1, 1. This is 1, this is 1. That means it will go to the memory state. That means it stores the previous value. What was the previous value? Previous value was 1. Fine. Then it is 1, 0. So it will again follow the R bar waveform, right? Then again 1, 1. So 1, 1, it will store the previous value. Previous value was this. Then again 1, 0. So what is 0? R bar is 0. So your output will still remain 0. Fine. And then your again memory state is there. So your output will still remain 0. And then your R bar becomes 1. So your output is also becomes 1. Output also becomes 1. And then again it encounters a memory state. So it will continue to be 1. Then again R bar becomes 0 and this becomes 1. So this will drop down. Fine. And then again it continues to be in the memory state. That means you do not apply any change after that. So it will hold this previous value, right? So it will hold this value. Fine. So your Q waveform will look something like this. So now can you see if any of the waveform are matching with this? We can see that yes, B would be the right option, right? So in this way, you can solve this kind of problems. Step 1, write NAND truth table. Step 2, write NAND latch truth table or formulate from this to this. Step 3, closely look at the waveform. To formulate cases and solve. Okay. So these are the 3 steps by which you can solve this kind of problems. I think this is very clear. So let's move on to the next problem. So it is stated that in the clock J and K waveforms for a positive edge triggered JK flip-flop are shown in the figure. The flip-flop output Q is 0 initially. So which option correctly describes the Q? Fine. So what is flip-flop, by the way? Let me just tell you briefly about flip-flops. See, latch was fine, right? With latch we can store one memory, but the issue with latches are that we need to change the inputs to get your output states changed. Okay. So many times it is not possible for us to change once the inputs are supplied to the pins of an IC. We cannot change the input, right? So what do we need to have some other controlling handle, right, to change it. So the way to do it is we use clock signals. If you have gone through the lectures, you must have seen that clock signals plus flip-flop, clock signal plus your latches will give you flip-flops, right? So if I have to say your SR latch plus clock would give you SR flip-flop. Okay. So SR flip-flop is the basic kind of flip-flop you can have. Now, then based upon that, you can build upon SR flip-flop and improve many other aspects, and you can finally arrive at JK flip-flop. Okay. So just let me briefly describe what how SR flip-flop actually comes about. So you know you have this contraption, right? You had this. Okay, you had this. So these were your flip-flop, right? Now just let me just remove this. You had this much, fine. You see, if you see the circuit, you had this thing. Okay. Now just let me call it A star and call it R star. Okay. And you have this Q and Q bar. Fine. So you know the truth table for this, right? A star, R star, Q, Q bar. This becomes 0, 1. Then your output is 1, 0. This is 1, 0. 1, 0 is 0, 1. You see, this is nothing but the same stuff. And your 1, 1 is your memory state. And 0, 0 not used, right? So this was the truth table. Now suppose I want to have another control. Let's say clock is another input. Output will read S and R value. Okay. That means when clock is 1, your S bar output will read S and R. Okay. S and R we have not defined. Some input it will read, let's say. And when clock is 0, that means system will be in memory state, right? System will be in memory state. Fine. Now you see you need this kind of operation that when your clock is 0, you need your S bar and R bar to be 1, right? Then only your this latch will be in memory state. And you want when clock is 1, your S bar would be, or rather say your Q will be equal to your current input, let's say S, and let's say that is S star bar. Okay. And your Q bar would be R, and let's say that is R star bar. Okay. So how we can do that? The way we can do that is Suppose you have this, okay, and now you pass your signal through an NAND gate. Fine. And suppose you are connecting your input like this. This is your clock, this is your S, and this is your R. Okay. So what was our NAND gate truth table? Let us recall this. Fine. If your clock is 0, right? Any of the input is 0, output will be always 1. So this will always be 1 and the system will be in memory state. Fine. Now let's say your clock is 1. That means you want to read the inputs. Okay. So if this is 1, then 1 1 will become. See, if your clock is 1 and your this thing is 1, then this will obviously be 0. Fine. You read this stuff. Now let's say this is your clock. So if your input is 1, output is just nothing but the invert of that. Fine. So this combination is playing here. And again, if it is 0, so it will be 1. Right? So in this way, you can, using the combinational circuits, you can design your flip-flops, right? So this entire contraption, is called your SR flip-flop. Okay. So what is the truth table? You have SR, you have clock, 3 inputs, Q and Q bar are the outputs. So whenever its clock is 0, irrespective of what is your S and R, your output will be, let's say this is N plus 1, this will be Qn and Qn bar, right? That means it is in memory state. Similarly, when this is 1 and this is 0, again, if both the inputs are 0, S star and Y star will always be 1. That means it will also be in the memory state. And if this is 1, then this will be 0 1, and this is this, output will be this. But again, this combination is not allowed. Fine. So this is the truth table of your SR flip-flop. Now this stuff has some issues. What are the issues? One issue is that you are wasting one combination, right? So this can be used. Okay. How can this be used? The way this can be used is, just let me quickly make the flip-flop. Okay. So this is your Q bar. This is your SR, and let's say you have some clock here. Fine. So the way you can use this is, you just have another input and crisscross, you connect the outputs like that. Okay. And if you see, you do this kind of configuration when S equals to 1, R equals to 1, and your clock is also 1. If you analyze it in the same way, you can find your output to be like this. Suppose this is your clock. And you will find your output to be something like this. It will change rapidly when the clock is on and these conditions are satisfied. This you can check from yourself from the concept which we have discussed. Also, you can follow the lecture video. Okay. So this way, this is called your racing, right? So this does not serve any purpose to us. So what we can do? We can, to mitigate this, what do we have? We have something called master slave configuration, right? Not useful. Solution. Can we make the change in Q once in a clock cycle? Depending on clock level, clock edge. Okay. Yes, we can. And the configuration is something like this. So this is your first stage of flip-flop. Fine. So you have your clock here. Fine. And then you have the similar stage at the output. Let me just copy it. Okay. So you have these stubs connected and your clock configuration is something like this. So this is your clock. This is, and this is called, by the way, your JK flip-flop. Okay. And you have these connections also. Okay. So this is your Q and this is your QR. This is called JK flip-flop, master slave configuration. Okay. Now it has many variants, right? You can have positive edge triggered, negative edge triggered. So I will suggest that due to time constraint, you can go through those in the lecture videos. So just let me tell you what a positive edge triggered JK flip-flop truth table will look like. Okay. You have positive edge triggered JK. You have negative edge triggered JK. You have level triggered JK. Okay. That means so far what do we have seen? We have seen that whenever your clock is high, then you read the samples, right? But what do we want now? Suppose you have your clock signal like this. Okay. So let's say if we read the clocks here, right? Whenever the clock is high, then that is called level triggered. But the issue with this is if whenever your clock is high, your input is changed, then your output will also change, right? This will cause into glitches or jitters in your circuit. Fine. Now, if suppose you are seeing only at the clock edge, that means whenever your clock is at the positive edge, and the way you can make the circuit is that suppose you have a capacitor and a resistance. Okay, so you can have your output something like that. Okay, so it will detect only the edges whenever the clock is changing from low to high, that is called positive edge. Okay, whenever your signal is red means whenever your clock is at positive edge, at that instant whatever your input whatever your states of the inputs are, it will transfer to the output. Fine, that is called positive edge triggered. So that is this case. And your negative edge triggered is whenever your sampling is done at this edge, right? High to low, this and this and this. Fine, these are your negative edges. Okay, so now we will discuss about this stuff, positive edge triggered JK flip flop truth table. Okay, so let's say this is your clock, this is your J, this is K, this is Q, and this is Q bar. By the way, symbol of the circuits are, this is your J. Let me just go this way. Say this is your J, this is your K, and this is your clock. Okay, this is your Q, this is your Q bar. This is the symbol of level triggered. Similarly, for positive edge triggered, the circuit will look like something like this. Okay, this is your clock. And for negative edge triggered, it will be a bubble. The same as positive edge triggered, but just with a bubble. Okay, so we are discussing about this stuff right now here. So whenever your clock is at positive edge, it samples the J and K input. Okay, if this is 0 1, your output will be, or let me start with this. If both are 0, your, and this is, let me say, n plus 1th sample. So your output will remain Qn and Qn bar. Fine. And if it is a positive edge, and if it is 0, it is 1, it will be 0 1. Positive edge is encountered. See, earlier we were writing clock as 1 and 0 because we were considering the level triggering thing, right? This is 1 0, your output would be 1 0. And if this is 1, this is 1, and both are 1, this case is same memory. This is something, and this is called toggling, right? Toggling means at this instant your output will just invert. Note this has changed, right? This has come to here. Okay, so this is the truth table of your JK flip flop when it is the clock is positive edge triggered, right? So keeping in mind this truth table, now let us go back to the problem and just copy this stuff. Okay, copy the entire thing, I guess. Okay. So just let us add another page. Okay, just let us do that. So let me just copy this thing again. Okay. So far, what are my positive edges? Positive edges are here, right? These are my positive edges. So my system will see whenever I have these edges, what is the status of my input, right? So if suppose I want to draw the output Q, this is my Q, okay, and this is T, let's say. So initially it was said to have 0, level 0, right? At this instant, it will encounter a positive edge at this instant. Fine. So what does it see? It sees that my output is 0. My input is 0. J is 0, right? So J is 0 means it will stay till J is 0 and it will check at the next. Let me just extend this positive edges because that is the time when we will be sampling. Fine. So till this point, it will hold the previous state, right? Because we got an edge, positive edge, but we saw that my input was 0. So it will keep my output at 0. Fine. Until the next positive edge has been encountered. So let me encounter the next positive edge. So at this case, what do I see? I see my J is 1 and K is 0, right? You see? So it will switch from 0 to 1. Till next positive edge. Fine. And at this next positive edge, what do I see? I see what is the input combination. My input combination is here 1 1. That means it is a toggling case. Remember, if it is a toggling case, then my output will be just flipped from the previous state. So output was previously 1. So at this stage, it will just toggle back to 0. Fine. And then till next in positive edge, we will wait. It will hold the value or store the value. Fine. Then at this point, what do I see? I see input is 0, J is 0, another and K is 1. So 0, 1 will lead to me output as 0. Fine. So it will allow me to hold the 0 value till this point. Fine. Again, I am repeating that this was 0, this was 0, and I have encountered at this place 0 0. Fine. So it will hold the state. Just let me copy the truth table. Okay. You just remember this one. When clock is high or when clock is having the positive edge, these both are 0 means memory state. This 0 1 0 1 will transmit, 1 0 will transmit 1 0, 1 1 will just change the previous state, and else whenever the clock edge is not encountered, my entire system will be at memory state. Fine. So this is until this we have memory. At this stage, what do I have? I have 1 and 0. Fine. So 1 and 0, the output will switch to 1 1 because Q is 1. If J and K is 1 and 0, it will hold till next positive edge, and at next positive edge it is seeing 1 1. That means it will toggle back. Then at next positive edge it is seeing 0 1. So it will remain 0. At next positive edge it is seeing 0 0. So at next positive edge we are seeing 0 0, right? So it will hold here. Fine. So if it hold here means it is a memory state till this point. At this stage it is again sampling and it is seeing 1 1. So 1 1 it will again toggle from 0 to 1. Fine. So it will hold till this value. So this value it is seeing again 1 1. So it will toggle back from 1 to 0. Fine. So it will go like this, and then at this place it will again sample 0 0. So it will hold it till this value, and after that it holds. Fine. So your output will be something like this. So this is, if I say 1 2 3 4 5 6 7 8 9. Okay. So at 2 and 6 you have positive pulses. So this is 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. So obviously B is not correct. This is also not correct, and this is also not correct. So A would be your right answer. Okay. So in this way you can cross check that. Just let me check whether I have received the right answer. Yes. So A is your right answer. Okay. So in this way you can check how this positive edge triggering works. You just need to be familiar with this table. This table you should be understanding very well. Then this is just very easy. Okay. So let's move on to the next topic. What is the minimum number of flip-flops required for a mod 40 counter? Fine. I am not sure whether my audio is coming through because I do not have any audience also, but and my laptop got shut down. Anyway, I think I am connected via my tab and I will continue. Okay. So just let me know if anyone can hear it or not. Okay. Anyway, I'll continue. Fine. I think my tab is working fine. Okay. So now this is asked, what is the minimum number of flip-flops required for a mod 40 counter? Fine. So you see, when my audio is going through. Yeah, I think I'm not muted. Okay. So let's continue. So if suppose you have n numbers of flip-flops. Okay. So what is the maximum number of counter? Maximum number of modulo counter you can have by the modulus refers to number of different states you can count. Okay, number of different states you can count. So if you have n number of flip-flop, so maximum modulus would be 2 to the power n. Fine. I think this is pretty simple to visualize, but the circuit part is not quite so simple. We'll discuss it anyway in the later section. So suppose you have mod 40 counter, right? So you know that 5 numbers of flip-flop will lead me to 32 mod max, and 6 number of flip-flops will lead me to 64 mod counter max. Fine. So what is the number of counters here? What is the number of flip-flops required for a mod 40 counter? It requires 6 numbers, right? Because anything more than 32 to 64, you need 6 counters, 6 number of flip-flops. Okay, so your C would be the right answer. So now let us move to problem number 4. Problem number 4 asks us about a D flip-flop. Okay, it gives us a thing of D flip-flop. By the way, what is D flip-flop? D flip-flop is nothing but you have something like this. Okay, you know about this SR flip-flop we have discussed, right? So this would be your D flip-flop, and let's say this is your clock, and this would be your Q and Q bar. Fine. So this is known as D flip-flop. Anyhow, your SR flip-flop does not use your this 0 0 or 1 1 condition. Fine, because your memory state is controlled by your clock, and 1 1 is not allowed in your SR flip-flop. So D flip-flop you can just avoid providing 2 individual signals, and you can use a NOT gate to just convert your S and R in a complement nature. Okay. So this is your D flip-flop, and the way to go about solving this thing is that to say suppose you have your, let's say this is, let's make a table. Okay, this is T or clock, let's say. Okay, and you have this your Q3, Q2, Q1, Q0. Okay, and then you have your just let me move it a bit aside. Okay, so you have your D3, D2, D1, D0. Fine. So you see your D2 is nothing but D3, right? Q3. So D2 is nothing but your Q3. Then it is Q2. D0 is your Q1. And your D3 is Q1, Q0, NAND, right? So this is your Q1, this is your Q0. So this is your Q0, Q1, and this will become Q0, Q1, and NAND, right? So you see, now let me take first clock cycle, okay? When clock is, just let me mention another column here. Let me say here, initial, okay? Initially, if your clock is 0, fine. So what was your this? This was your so your 1100, right? 1100 was your initial stuff. Fine. What was your D? D, by the way, D would have become this Q1, Q2, sorry, Q1, Q0, this 0, 0, and this 1. Fine. This is 1. So this will shift to here. This will shift to here. And this will shift to here. Fine. 1, 1, 0. Fine. You see how you are getting the initial state? Because initially your D will be computed, right? These things will be computed. D will be whatever you have in your Q1, Q2, Q3, and Q0. But your Q will not be computed until unless you have your clock pulse. That means when clock is high, then only your data will be transferred from D to Q. Fine. But whenever clock is not high, your D can as well be computed. Fine. So this is your initial. Now let me take first clock pulse and I will consider 1 and 0. Fine. Then I will have second clock pulse. Okay. Let me add another page. Then I would have third clock pulse, 1 and 0. By the way, how many they wanted us to calculate? After 5 clock pulse, okay? Then I will have fourth, 1 and 0. And continuing it to the next page, we'll have fifth, 1 and 0, okay? We will see. So, whenever your first clock pulse is applied, right? Then this data, whatever was previously stored in the previous clock pulse, that will be transferred to your Q3 Qs. That means your this one will be transferred here in the next clock pulse. Fine. And immediately your D3, D2, D1, D0 is also calculated based on this. So what will be that? Your 1, 0, and will be 0 and it will be 1. And then 1, 1, 1, right? Your this and the NAND operation will be here. This will be here, this will be here, and this will be here. Fine. Now, when the clock goes to low, the Qs will get stored in the same fashion because Qs will not change whenever your clock is low because it is a level triggered, right? It is a level triggered. And how do you know it is a level triggered? You know this from this symbol, right? Because there is no this arrow sign.
And similarly, your D3 computation will remain same. Fine. Again, when your clock pulse will become high, the second clock pulse arrives, your output will be simply this. Because this will come to here. Fine. And accordingly, your D3, D2, D1, D0 will be computed. Fine. So one will be coming here, one will be coming here, and one will be coming here. Fine. And what about this? 1, 1 would be 0. 1, 1 would be 1, and this would NAND operation would be 0. Fine. So same thing will be happening here also. Now, whenever it is again third clock pulse arrives, this output will get the value from its D's, right? Its inputs. So again, this is 1. So basically, this comes at here. Now, accordingly, this 1, 1 will become 0, 0, 1, 1, right? This again, I am telling this goes to here, this goes to here, this goes to here, right? And this operation, NAND operation, will be stored here. Fine. So again, whenever clock is low, you have memory state. So you have the same stuff. And whenever your fifth clock pulse will arrive, your Qs will fetch the value from previous Ds. And your now output will be, this will be 0 from 1, 1 and this will be 0, 0, 1. Fine. Then again this, and this will be step here, 0, 0, 0, 1. And again 0, 1 would be 0, so it will be 1. And then again 0, 0, 0. Because this 3, this 3 will be going to this 3. And these two NAND operation will be coming here. Fine. And whenever clock is 0, you have this. Fine. So the question is asked that what is the state of the counter after 5 clock pulses, right? So after 5th clock pulses, we see the state of the counter is 0, 0, 0, 1, right? That means Q3, Q2, Q1, Q0 is nothing but 0, 0, 0, 1. Fine. So your output would be 0, 0, 0, 1. Okay. So B is your right answer. Fine. Now let's move on to problem number 5. Again, the same thing they are asking, but they want us to find out the modulus of the counter. Fine. Now follow the last problem solution. Okay. So we have seen that so far we did not have any repetition, right? We have individual distinct states. What are the states we have found so far? We have this, then this, then this, then this, this, this. So let us continue for some more time. So 6th one, you see 1, 0, 0, 0 will be here, and whatever your output will be, this 0, 0 will become 1, then 1, 0, 0. Fine. Then again, if I go up to the 7th clock pulse, what do I have? I have here 1, 1, 0, 0, and this 0, 0 becomes 1, 1, again 1, 0. Fine. So 1, 1, 1, 0. So again, if we do the 8th pulse, we have 1, 1, 1, 0. So we have here 1 0 would be 0, then it is 1 1 1 1. Okay, so I think we are now repeating the steps. Okay, because we have this also and this also, fine, and this is the same thing, this is the same thing, this thing 1 1 1 1 1 0 0 is the same starting point, right? And see, the next sequence is also 1 1 1 0. So 1 1 1 0. Fine. Now we are having a repetition. So what are the distinct states you are having? Distinct states you are having is that 1 2 3 4 5 6 7. Fine. And then this is again 1. So you have 7 distinct states. Okay, so your it is a basically mod 7 counter. Fine. So this is how you find it. So the modulo of this counter is 7. Okay, just let me check whether I have found it correctly. Yes, it is a mod 7 counter. Okay, in this way you can solve this kind of problems. So now let us move on to problem number 6. Problem number 6 is telling us that consider a BCD counter shown in the figure. Define D to be the decimal number. Okay, D to be the decimal number corresponding to the binary number this. Okay, D is the MSB and A is the LSB. We want to design a decoding logic such that X is 1 for this. Okay, fine. So this is pretty simple. I think this is nothing to do with your sequential logic. It is nothing but this is a combinational logic part, right? And the way to design it is you draw a Carnot map. Fine. Last week I have shown you how to draw Carnot maps, right? So what was your MSB? MSB was D, right? D, then C, then B, then A. Fine. 0 1 1 0 1 1 0 0 0 1 1 0 1 1. Fine. So we have X is 1, output is 1 when D, let me just specify what are the values here. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, so what do we have? First thing is that X is 1 for D is 2 4 5 6 and 0. Okay, means 0 2 4 5 6. Fine. Okay, not 0. 0 for these things. Okay. Fine. We have only 4 cases for which output is 1, 2, 4, 5, 6 and 0 for 0, 1, 3, 7, 8. So 0, 1, 3, 7, 8, 9. Fine. And 10 to 15 should be taken as a don't care conditions. Okay. Now we need to simplify this. And how do we simplify this? We have already seen it in the last week, how to simplify this kind of circuits. We need to take the maximum possible cluster of ones, right? Including don't cares. So we see we can make here 4 number of stuffs in a one cluster, and here also we can make 4 number of things. Okay, so these two are the combinations. So what is your x? Your x is nothing but here common is C and here common is B bar, plus in this case it is B A bar. Okay, so your x is nothing but A bar B plus B bar C. Fine. So there is nothing sequential involved in this. You have only your combinational logic simplification using Carnot map. Okay, so A bar B plus B bar C is your right option. So B is your right option. So next, moving on to a 3-bit binary up counter with an output this Q2 being the MSB. Okay, so let us see how to design an up counter. Three-bit binary up counter will be something like this. Okay, so these are your inputs, these are your outputs. Let me just have more space here. Okay, so you generally connect your up counter like this. This you set to 1. This is nothing but your JK. This is your clock. This you keep at 1. Okay, so this is your Q0, this is your Q1, this is your Q2. Okay, this is your Q2 bar, and this is J0 K0, J1 K1, J2 K2, Q1 bar, Q0 bar. Okay, so this is nothing but your up counter. Now see the way it works as, you can easily visualize that the system is made sure that it will only work in a toggling mode. Okay, because whenever your clock is at having a negative edge and your input are always having 1-1 configuration. Fine. Now suppose this is your clock signal. Okay, just let me draw it a more smaller version. Two, three, four. Okay, so this is your clock signal. Fine, and these are your negative edges. Okay, so what would be your Q0? This is your Q0, right? So your Q0 will remain same as previous value, and at the negative edge it will toggle. Fine, and then again at the negative edge it will toggle. Then again at the negative edge it will toggle up, then toggle down, then toggle up. Okay, so this is your Q0. Fine, now you note that Q for this is the 0, this is 1, this is 2. For your flip-flop number 1, your clock input is nothing but Q0, okay? Q0 access clock to FF1, okay? So now similarly, if this is, let me show it in green color. So we would see the negative edges here, fine? Because this is the clock signal for a negative edge triggered flip-flop number 1. So your toggling will start here, fine? Again, it will go to this and then follow for the next stage. This is your Q1, fine? Similarly, what would be your Q2? Your Q2 will see this edge, right? Fine. So you notice that the time period is getting doubled, right? That means if this is your, this time period is T, then this signal has a time period of 2T, fine? And this signal has a time period of 4T. So this signal has a time period of, this is 40 means half time period. That means time period is here 80, fine? So if your time period is doubled, then what is the frequency sense? Frequency is half, right? So if this has frequency F0, this will have frequency F0 by 2, this will have frequency F0 by 4, and this will have frequency F0 by 8, fine? Now, what is given? Given is that your clock frequency F0 is 8 kilohertz, fine? So let me say this is FQ0, right? This, let's say this is F. Okay, let me say this is F. So this will be F0, this will be F1, this will be F2. Okay, so if your F is 8 kilohertz, so your F0 will be 4 kilohertz, that is of Q0. F1 would be 2 kilohertz, that is of Q1, and F2 would be 1 kilohertz, fine? That would be of Q2. So what is the question? Question is that if a logical function x equal to Q2, Q1 is implemented, what is the frequency of x? So you can simply see from your signal systems knowledge that your frequency of x would be minimum of, if it is if Q1, Q2 are just harmonics of each other, right? So minimum of frequency Q1, Q2, that is 1 kilohertz, fine? So frequency will be 1 kilohertz for this function, fine? Similarly, the same problem is given here, just they have changed the function. So x is now Q1 and Q0. So what was the frequency of Q1? Frequency of Q1 was 2 kilohertz, fine? And what was the frequency of Q0? It was 4 kilohertz. So obviously, frequency of x should be 2 kilohertz here, fine? So you just need to know how your up counter works, and this can be used as a frequency divider, right? So moving on to problem number 9. again, this is similar to problem number 4, but here instead of similar to problem number 4, right? And instead of D flip-flop, here we have JK flip-flop, fine. And instead of level triggering, here we have negative edge triggering, fine. The very simple way to do this is, again, make a table, right? First, I would like to tell you that if it is a clock pulse, okay? Suppose if it is a clock pulse, so this is your negative edge, right? So what we will consider? We will consider from previous edge to this point, that means this point, just before T, say this is TK, okay? So this amount we will consider as TK minus, and just after TK, we will consider the time has to be TK plus, okay? Now we will make a table of it. So just let me copy the circuit. Okay, let me just copy the circuit here. And what we'll do, we'll make the same kind of table. This is clock, say T. This is Q0, Q1, Q2, J0, K0, J1, K1, J2, K2. Okay. This portion we will consider it for TK minus. Okay. And then again we will see what is the status of my these three things. Q0, just let me okay. So this is for TK minus, and let's say this we want to do for TK plus. Okay. So what is the question? Question is that initial figure is 0, 0, 0. Fine. So initially we have 0, 0, 0. Okay. So if initially we have 0, 0, 0, what is your, just let me zoom the figure. Okay. You see your J0, K0 is nothing but 1 always. Fine. This is nothing but always 1. What is your J1, K1? J1, K1 is nothing but it's connecting to this, means this is Q0 bar. Okay. So Q0 bar, this is also Q0 bar. Fine. What is your J2, K2? This is your Q1 bar and Q1 bar, and this is your this is, and another one is this Q0 bar. Okay. So this is Q1 bar into Q0 bar, both the cases, J and K. So this is Q, both are Q1 bar, Q0 bar. Okay. So now when you're, now when you have T1. Okay, let's say T1 means you have encountered your first negative edge of the clock pulse. See, we have mentioned this point we are considering at the negative edge, we are considering Tk. That means T1 will be here. What about J0, K0? It will be 1, 1, as it is not changed. So this will remain 1, 1. Fine. What about your J1, K1? J1, K1 is nothing but your Q0 bar, right? So your Q0 is 0. Fine. So this will be 1. And whatever is your J2, K2 is Q1 bar and Q0 bar. So 1 and so it will be, both will be 1. Fine. Now you know that your truth table for JK flip-flop with a negative edge triggered is something like this. Whenever you have a negative edge and whenever these are this, you have a memory state, right? And the negative edge, you have 0, 1, Q1 is 0. Negative edge, you have 1, 0, your output is 1. Whenever negative edge and 1, 1 is there, your output will be Qn bar, right? It will toggle. So this is memory. This is toggle. Fine. So now you see what you will observe. You will observe this. What are the inputs? And you will see previous one, and you will just put the values here. Fine. So it is 1, 1. That means it has to toggle. So 0 will be 1. Again, 1, 1, 0 will be 1. 1, 1, 0 will be 1. Fine. So for the negative, for the next cycle, this will be your input. Fine. And similarly, J0, K0 always 1, 1. This will be 0 because Q0 is 1. So 0, 0. And again, this will be Q0 is 1. That means it will be 0, 0. Fine. So what is your output? This should be toggle. So 1 will toggle to 0. 0, 0 is your memory state, right? This is your memory state. So it will hold the value 1. And this is also 0. So it will hold the value 1. Fine. So again, T3, let us calculate 0, 1, 1. Fine. This will remain 1, 1. What about? Sorry, I think due to some internet connection, just let me share the screen again. Okay. I think due to some internet connection, we have lost a few minutes. Okay, again, I will repeat. Fine. So what we are discussing question number 9. Fine. We are discussing how a JK flip-flop with negative edge triggered works. Fine. So now what is the case? We were at third clock pulse, right? So if it is 1, 1, then we have a toggle here. Fine. It is 1, 1, we will have a toggle here, and it is 0, so we will conserve the state, previous state. So again, T4, we have 1, 0, 1. Fine. So 1, 0, 1 will have this 1, it will be 0, 0 because, sorry, this will be 1, 1 because it is not changed, right? It will always be 1. And this is Q0 bar, that means it will be 0, 0. And Q0 bar and Q1 bar, it will also be 0, 0. That means only 1 will toggle to 0, 0 will remain 0, 1 will remain 1. Fine. So at T5, you have 0, 0, 1. Again, this will remain same because it is a fixed supply. This will be your 1, 1, and this will be your 1, 1. So this will also be 1, 1. So every bit of this will toggle. Fine, right? So you have here 1, 1, 0. Fine. Next again we see 1 1 0. So 1 1 will remain same. This 1 1 will be Q0 bar. Q0 is 1, so it will be 0 0. And here Q0 bar, Q1 bar, right? So it will be 0 0. So 1 1 means it will toggle. First Q0 will toggle, Q1 will remain same, Q2 will remain same. Fine. So now P7 is your 0 1 0. Fine. So now similarly, we can write that this will be the case. It will be 1. It will be toggling, so it will be 0. It will be remaining same, so it will be 0 0 1. Fine. Now let us see T8. So we have 1 0 0. So 1 1. It is 0 0 0 0. So first bit will toggle, then it will be same. It will be same. Fine. So now see, after 8 cycles, we have come back to the first bit, right? So when I have your 9th pulse, I will have again 0 0 0, and this stuff will again continue in a ring way. Fine. So now let us see what is the question. The question is, what is the state after 3 clock pulses? Fine. So after 3 clock pulses, what do we have? After 3 clock, this is the first clock pulse, this is the second clock pulse, this is the third clock pulse. Okay. So after third clock pulse, we have this. So Q0, Q1, Q2 is 1 0 1. Okay. So the output is, we have Q2, Q1, Q0 will be 1 0 1. Fine. So C is the right option. Fine. So moving on to the next, again the same question. What is the state after 5 clock pulses? Okay. So this is third, fourth, fifth. This is my 5th clock pulse. Fine. So I have Q0, Q1, Q2. After 5 clock pulses, this is nothing but 1 1 0. That means my Q2, Q1, Q0 to be 0 1 1. Okay. So D will be my right answer. So what is the modulo number of the counter considered in Q9? What will be my modulo? 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 distinct states we are having. This is again 1. So we have mod 8 counter. Fine. So modulo of the counter would be 8. See solution in previous question. Okay. So question number 12. If the initial state is 0 0 0, what is the state after 28 clock pulses? Okay. So 28 clock pulses means you have 0 to 8. Sorry. 28, right? So you have 1 to 8. Then you have 9 to 16. Then you have 17 to 24. Then you have 25 to 28. Fine. So this is nothing but 1 to 8. This will be also 1 to 8 because it is modulo 8 counter. This will also be 1 to 8. Fine. 25, 26, 27, 28. Right. So this will first to second, third, and fourth. So 28 will be whatever my output is after 4th clock pulses. Output after 28th pulse is equivalent to output after 4th pulse, right? So what was my output after 4th pulse? It was 0 0 1. Okay. So Q0, Q1, Q2, 0, 0, 1. That means my Q2, Q1, Q0 would be 1, 0, 0. Fine. So D will be my right answer. So what about question number 13? If the Q2 output of the counter is described in Q1 is considered as MSB, okay, Q2 as LSB, okay, Q2, Q1, Q0, fine. So if we see, this will be just reversed, right? This way, this is MSB, this is LSB. So this is 0, this is 7, this is 6, 5, 4, because 1, 0, 0, right? 0, 1, 1, 3, 2, 1, and 0. So it is a down counter. We can readily see that. First observation from Q9 table. A, it is a down counter. B, it is a 3-bit counter. C, it is a synchronous counter. By the way, what do we mean by synchronous counter? That means same clock pulses are applied at the all the levels of the flip-flops, right? Synchronous counter. And also it is a binary counter, right? We have seen that it has counted from 7, 6 onwards to 0 and then back to 7. Okay. So D would be my right answer. A 3-bit binary synchronous down counter. Okay. So moving on to problem number 14. So same problem as problem number 9. Same problem as problem number 9. Okay. So this I will assign as you can solve this in the similar way, right? I will not solve it, but I will post the solution. Okay. Solve it in the same manner. Also, we are almost at the end of second hour. So this you can do in the same way, right? Note clock is positive edge triggered. Okay. So you need to consider this thing. Okay. Whenever your inputs are up, fine, you need to consider those edges, positive edges. Input, whenever your input is changing from low to high, that is your positive edge. At that stage, what is your status of the input? So you can assume this much as Tk minus 1, Tk minus. At this instant, you assume as the clock pulse, and at this instant, you assume at the Tk plus, and you prepare the table in the same format, and you will be able to find out the answer. Okay. So I will just tell you the answer to this question. Just let me see if I had solved it. Okay, so you will find out that it is a modulo 6 counter. Okay. Fine. You note that at this point you will have this your JB and KB is equal to QC XOR of QA. Fine. And your JC is nothing but it is your JC, right? It is the end input of QB QA bar. Okay. And your KC is nothing but QB bar. Okay. You note this point, you just make the same table in the same manner. You will find out the answer very easily. And similarly, this would be your answer. Okay. Do it in the similar way as shown in problem 9 to 13. Okay. So this is how you solve these questions. Okay. So let me just again revisit what we have discussed today. So we have discussed basically what are the sequential circuits. What are the sequential circuits? And what is the difference with combinational circuit? Because it is having a memory in the feedback path, right? And the basic building block of any sequential circuit is a latch. So we have discussed SR NOR latch in detail. And then also we have started solving a problem, started our problem solving session with a NAND latch problem. Fine. Then we have seen why do we need flip-flops and what is an SR flip-flop and what is an JK flip-flop, what is a master slave configuration, what is positive edge triggered, negative edge triggered, and we have come up with the truth table and then we have solved the problem, right? How a positive edge triggered flip-flop will look like. Then we have discussed what is the meaning of this modulus. Modulus means number of independent states, right? Different states of output you can count. In that way, you can find out the modulo of your counter. And then we have discussed briefly about D flip-flops and solved the problem that how it is counting, and also we have calculated the modulus of this counter. Fine. So next we have discussed a combinational circuit. At the very beginning, when you read the question, it seems that it is a very difficult question, but it is not. It is a simple K-map simplification. Fine. It will take you just 1 or 2 minutes if you have the concepts clear, right? So problem number 6 is like that. Then we have gone to problem number 7, where we have discussed how an up counter works. It works on the principle of frequency division, right? So now you see, if you take this Q0, Q1 and Q2 and make a combination out of it, by properly assigning the MSB and LSB, you can count from 0 to 7 with this counter, right? Because it is a modulo 8 counter, 3-bit binary up counter, okay? So we have seen how the frequency division works, and if we make any combination with the outputs of each stages, we can calculate the frequency of that signal, right? Then we have discussed problem number 9, which is the major problem which we have discussed today. In this problem, it is very simple. What you need to do is you just need to remember what is positive edge triggering and negative edge triggering. And you should know how a JK flip-flop table, when positive edge triggering, negative edge triggering, or level triggering, how the table looks like. Fine. And you then make a detailed table of the states. How, if we change from one input to another input, how will your counter outputs will change, right? And if this detailed state table, after several calculations, you will find that after some time that these states are repeating. So at that time, you will find out what is the modulus of this counter. Also, after any clock pulses, what is the status or state of your output, you can calculate. Fine. So once you prepare this table, you see that from problem number 9 to problem number 13, it just took around 2 to 3 minutes to solve, right? Then similarly, we had another problem with positive edge triggering of the JK flip-flop. But that thing we can easily just do on the same principles, right? So this I expect you will do. I have also mentioned how to proceed about it. The same thing, you see, this JA, JB, JC, JA and KA are 1 for eternity because it has been shown here. It has been shown here to be 1, fine. And JB, KB is this expression. JC and KC is this expression. Similar to this table, you just draw a similar table and you compute the states, and you will find out easily what is the modulus of the counter, which will come out to be 6, and after any number of clock